Well, good morning. Thanks for joining us today at the Block Breakfast Club. This is the third in a series of webinars that we're holding about networking in healthcare. And today we're talking about designing the always-on healthcare network. So I'm Matthew Mahoney, I'm Director of Digital Transformation at Block, and I'm joined by Joseph Tabberer. So Joe, would you like to introduce yourself?
Yeah, hi everyone. I'm Joe Tabberer from Block. I'm a network architect in Block's enterprise networks practice.
Okay, thanks, Joe. So throughout the webinar, we'll be holding a Q&A session in the chat, so please feel free to chip in and ask questions as we go through. And we will have a sort of a pause at the end where you can fire over any questions to the expert Joe, and hopefully we can answer those on the call today. So if we can have a look at the agenda, Joe. So we've done the introductions. We're going to talk about connectivity in healthcare and high availability, leveraging wireless for high availability, and then there's a brief kind of not so much demonstration, kind of more of a use case and an example of how Thousand Eyes has been applied to help us diagnose an issue. And also, as I said, there'll be the Q&A session at the end.
Okay, should we kick off? So Matthew, just to introduce the topic, I wondered if you could just tell us a little bit about how important availability was in your experience in the healthcare network.
Yeah, incredibly important. Yeah. So for those of you who don't know me, I'm an ex-CTO in a large NHS health board, about 16,000 staff, a wide range of sites, and for us, really, it was incredibly important to be able to keep information flowing and to provide clinicians with the data and information they need at the point of care to do their jobs safely and to make sure that we're not causing any patient harm. So it was a real challenge, because I'm sure if you work in healthcare, you can probably imagine there's quite a wide range of quality of estate in hospitals and healthcare, and it's very, very challenging in terms of investment as well to be able to provide that kind of availability. So if we had outages, they were quite serious. They can affect things like your electronic patient records, your sort of laboratory systems, your imaging systems for radiology, and other things like the integration engines as well. So you might not lose availability of your pathology systems, but the integration engine that sends the results back to your system might get interrupted. So you've suddenly got results queuing up and backed up, and you might have to restart web servers, that sort of thing. It became really, really challenging. Some of the other areas that obviously availability will affect are things like telephony, bedside monitoring, and even down to like patient entertainment systems or guest Wi-Fi can be impacted by this. So if you start to lose the network, you start to have a really, really significant impact on healthcare and potentially on the patient experience and patient outcomes even as well. The outages and the impact of the outages can be quite severe at times. So without the right information access at the point of care, it can lead clinicians to a position where they have to make decisions where they're not fully confident in what they're doing, but they're doing their best with the information they've got at the time. But it would be a much nicer place if they had all of the information they needed at that point in time. It can also stop the system working efficiently as well. So it can start impacting things like admissions, discharges, and transfers, which slows down the kind of flow of the healthcare environment. And if you're having to revert back to paper records during these times as well, where you've got an outage, that does mean that all that information has to be recaptured or rekeyed, which again is just creating additional work, additional impact for the team, and really kind of like impacting the efficiency for healthcare. I think that the organisation I work for had a really wide range of sites. So you'd have like quite specialist critical care centres, acute hospitals, down to resource centres and kind of clinics out in the community, which you've got to obviously balance the kind of levels of availability that you need at those sites, with obviously the acute kind of setting needing the most kind of investment in availability to perhaps, I wouldn't say it wasn't important, but we would have less of a priority for investment around some of the smaller clinics and resource centres out in the community. But still, if you lose connectivity there, you're still potentially impacting patients. You're still potentially causing appointments to be missed or cancelled, and that can be quite upsetting for patients. So we never want that to happen. And it's really challenging to get it right in healthcare. I think some of the things that when we think about availability, we don't necessarily just think about unplanned events. There are planned events as well. So, there's a constant need to refresh the hospital network and the equipment, and that can lead to downtime as well. So that can be quite challenging. And it's never a good conversation to say, hi, we're going to come to an ED department, and we're going to turn it off for a few hours while we upgrade the network. So you have to get, the clinical teams on side, and that can sometimes mean that they have to bring in additional staff to cover and to kind of overcome the additional workload that not having access to IT means. But I think it's definitely a challenging subject, Joe.
Yeah, absolutely. So we'll just take a look at what availability means. The basics. So a network that's designed for high availability is reliable, and it's tolerant of some individual failures. We can't expect a network to be truly always on, unfortunately. I know that's the title of today's webinar, but what we're looking at is getting as close to that 100% uptime as reasonably possible. Within a network, obviously, there's a number of different components in there, and those components will fail. Those individual components will fail, but we're aiming for as close as we can get to that 100%. And when we think about availability, we do use that percentages of time that a system is operational, to indicate what level of availability we're aiming for. And you can see on the slides here, typically this is represented in a number of 4 nines of availability. Just under an hour's worth of a downtime per year is what we're aiming for, and then beyond that, 5 nines is getting into the league of mere minutes. So yeah, that's truly what we're aiming for, as high as possible, closest to that 100%.
What types of outages can we see in networking?
So we can categorize it into 2 basic types, really. So we have unplanned outages, which could be individual device failures within our network. You can see in this topology here, we've got a traditional 3-tiered topology: core, distribution, access, and we've got a device failure here and a link failure here. And in a non-resilient topology, then this could result in outages. So device failure could be a power failure, which is quite common, or a link failure could just be a fiber cut, somebody just knocking a transceiver when they're working within an equipment room.
Yeah, genuinely, like in my experience, I've had, I won't name the company, but a large telecoms provider going into data centers or going into comms rooms and just disconnecting stuff, not necessarily realizing what the impact of that is. And I think that these things are never planned, really. I mean, you don't want them to happen. As you said, we can also have like the power failures as well. So in a hospital and a care setting, you've got a lot of generator tests. You've got a lot of kind of like resilient power tests for the site, which are going to impact your computer rooms as well. And when we think about those failures, with those, I'm going to call them the Batman splats because I'm old enough to remember the original Batman. If you've got one of those affecting your connectivity to the network core in the pathway, ultimately, if you're at that access layer and your path back up to the core is impacted, you're not getting on the network. It's essentially what we're saying, isn't it?
Yeah, exactly that. Like you say, in a sort of dynamic environment, there's a lot going on. We're likely to encounter some kind of unplanned failure at some point in time. And if we haven't planned for that within the network, then that's going to result in downtime.
Okay.
And then our second type of category is planned outages that you mentioned earlier. So there's often a requirement to replace a network device. It's reached the end of its life cycle. It's obsolete. We need to take that out of the network. That can be a big event if we haven't got any resilience built into our network. If we pull it out, perhaps we're going to require a couple of hours worth of downtime or an hour's worth of downtime whilst we're replacing the device. And then another planned event is a software upgrade, and software upgrades are important in themselves for high availability. They protect us from potentially seeing any software defects that may exist in older software, or running into any security vulnerabilities that have been identified within a particular software release. So it's important we do that, but a software upgrade typically requires a device reload, and that's potentially going to result in downtime again if we haven't got resilience built into the network.
Yeah. Okay. Thanks, Joe. So, I mean, how do we build a network that has redundancy and can survive these types of outages?
Yeah. Okay. So I mean, we'll begin with the fundamentals, and that's within the physical design, we need to make sure that's redundant. We need to remove any single points of failure that exists within the network. We need to as you can see here, deploy multiple devices in parallel. What does that mean? It means that looking at our three-tier architecture again, the core distribution access, we've got multiple devices in the same network layer. So we've got two core switches, two distribution, basics of course, but and we need to ensure that we've got resilient interconnectivity between each of these layers as well. So we've got multiple uplinks from our access layer switch going to our distribution. So from a physical perspective, we're able to withstand the loss of a single network device within the core distribution layer, and a single uplink from one of the devices down in the access layer.
Okay, but I can see we've kind of got the interconnectivity between all of the devices there. If we're at the access layer and we're connected to the switch on the left, um, and that fails, you still don't have connectivity, do you? Just to be clear on that, if you see what I mean. Yeah.
Yeah, yeah, that's right. If you're a wired endpoint, a workstation, for example, it's connecting to an access layer switch, and you've only got a single connection. Yeah, if that goes offline, then you've lost your connectivity until it's restored. So, yeah, we need to look at some of those ways that we can provide that increased uptime at the access layer as well.
Yeah, so I guess my experience in healthcare, we had a range of sites. Some of the hospitals were built, before IT was even a thing, really. There was probably large 5 MB hard drives being loaded onto Boeings at that point when those
Yeah.
hospitals were built. The more recent stuff that I've been involved with, there's probably about 10 or 12, I think, sites that were constructed in my time during the last 10 years or so in the health board, and they were designed buildings with high availability and resilience inside them, so you could get this kind of connectivity.
Mm.
Some of the older sites were, they were so old that IT wasn't around, and they were a bit more of a challenge, let's just put it that way, and they were generally, constructed with non-modern techniques. So it made it an interesting landscape within which to operate. But I think we did our best. I think we're probably the way describing that.
Yeah, and we appreciate that it's not always going to be easy to provide that physical connectivity. Maybe we can't get those dual fiber links that we need from our distribution area over to our access in all cases. I mean, we should definitely strive to do that. But yeah, there are alternative topologies, the access layer that can be deployed, that still provide that resilience, where we can't have this very simplistic architecture.
Okay, great, thanks.
So yeah, I mean that was the absolute basics. I just want to go through some of the logical topologies that we commonly see nowadays as well. So we looked at the network design from a physical point of view. We talked about building in redundancy there in terms of multiple devices and multiple links. Now, just having a look at the logical topologies, I'm just going to go through a few that I commonly see in customers' networks that we're working with within healthcare. So first off is this flat layer 2 network. So again, we're just using the same core distribution access physical design, as you can see, but here we've got layer 2 all the way down from the core layer, which necessitates the need to use spanning tree protocol to block any redundant paths. Sorry, I've skipped ahead one. Which means that we've got not using all the capacity within our network, but we do have the failover capability. This you should say is an older type of topology. We see this less and less now. The reason being is because the convergence times can be quite high. Up to absolute worst case 50 seconds, and
What's the impact of 50 seconds? You can sort of survive that at home probably if you're watching Netflix.
I don't know. I'm not sure in our household
Yeah, that's
nowadays.
fine. Yeah, with four kids, watching it or whatever. But yeah, so in terms of the impact on connectivity, 50 seconds. That sounds like quite a long time in a healthcare setting. What would that
Yeah.
translate to?
It, nowadays, I mean again, it's worst case, but that would be somewhat of a lifetime. So some applications are pretty tolerant of network loss. However, others are very sensitive. At the other extreme of the scale, you've got voice traffic, which is real-time traffic, which is really sensitive to any loss or any delays or any deviation, any jitter. And that, for taking voice example, that would mean distorted or dropped calls, depending on the length of the time it takes the network to converge. But yeah, it would be a noticeable impact.
So 50 seconds, that call's gone, isn't it, really? I think, the best case scenario, a bit of disruption to that call, 50 seconds, the call's gone. What about, I think you said applications, it's going to depend on the way the application's coded.
Yeah.
I'm trawling my distant memory from doing application development a long time ago, and just depends, I suppose, on how the application works and whether it's kind of maintaining a persistent connection or just doing calls to the database as and when it needs to. I guess the reality is that in a large setting with a large number of people using applications, there are going to be people who are impacted in that situation because they're going to be making calls to the application quite consistently throughout throughout that 50-second potential period. What about file
Yeah.
shares? You're copying files, you're trying to browse the web or use SharePoint or a Teams call. Presumably they're all impacted too.
Yeah, it may be less noticeable for people who are, browsing the web. Yeah, Teams, obviously, again, we're using voice and video, so that's likely to be impacted. But yeah, some of them, some of the some of the protocols we see used within healthcare for applications they do have some built-in tolerance, quite high timeout values for when connections are lost and the ability to retry a number of times before
Yeah.
messages have to be manually resent and things like that. But yeah, absolutely, that would be an unacceptable amount of time in today's networks.
Okay, so that's gone into my mental risk register. What's the mitigation, Joe? How do we fix this?
So we're just kind of moving on, maybe in the timeline a little. We see this kind of logical topology quite a lot now with our healthcare customers, and this is sort of an evolution for that design. Again, we've still got a flat layer 2 network. However, this time what we've done is we've got a virtualized core and distribution layer, and what does that mean? It means that we've taken two physical switches for our core layer, and we made them appear to the network as a single logical device, and that enables us to build a topology that's free of any spanning tree block links. So we can use all of these links. We can have multiple uplinks connected between layers, and they're bundled together to give us increased bandwidth between the layers, and we can use all of those connections. Furthermore, it means that we can have up to sub-second convergence as we lose individual links or devices in this kind of topology. So that's obviously a big step forward from the kind of topology we're looking at
Yeah,
before.
just thinking that through then. So unless you're connected to an access layer switch that's failed, you're in theory not going to notice an issue.
Yeah. A lot of the time, these individual link failures, for example, nobody's gonna notice that impact. It's much less of an impact from the topology we were looking at before. There is, I would say, so up until recently, and talking with a lot of vendors, that this would still be a best practice design for certainly a smaller scale environment. There are some downsides, I say, and we'll look at another topology in a moment. This design scales vertically, which means that we can only have a single pair in our core or distribution layer, and in order to scale this design, we need to add in more ports to increase capacity if that's required. So that means that you need to buy more ports up front, and perhaps never make use of them. So it could be that we've got a couple of big chassis there in the core layer,
Mm.
loads of slots in there, and big capacity for growth, but maybe we'll never make use of that. And the other downside is that whilst it's really uncommon, well, I'll say it is uncommon, issues can occur during what's known as in-service software upgrades of these devices. So the idea being that we can upgrade a pair of these switches without having impact to the rest of the network. Sometimes that doesn't go to plan, or sometimes there's that we come across software defects where we have a virtualized pair of switches, and that can result in the loss of the pair of switches. Now, these are rare events, but that means that until we can restore that pair, that we may have a network outage until that they're both restored.
Yeah, so I mean, I suppose when you say it scales vertically, we've got a bit of a challenge there in terms of the size of campus that you're operating. So, in my experience, that's quite common in being used.
Mm.
Other approaches have been used as well, but depending on how much you've got of that kind of like access layer and that distribution layer, that's going to really determine whether that works for you or not, and how you would implement that.
Yeah,
Um,
yeah,
yeah,
yeah.
so go on then. What's next? Because we've got we've got some options, I suppose.
Okay, yeah. So the last one that we'll look at is the routed access design. Okay, so this is again, we're looking at the same three-tier topology, core distribution access. The difference here is that the layer 2, layer 3 boundaries, you can see at the bottom, has moved right down to the access layer, or in some cases this is a distribution layer. All of these interconnections between these devices are all routed links. They're all layer 3. In a simple routed access design, VLANs aren't extended across the campus network, but instead they're localized down at the access layer switch. A routing protocol, interior gateway protocol, is used to distribute reachability for any of our user networks here. Again, like the last design, we don't have any links that are blocked, so we don't have to, because we don't need to worry about any layer 2 or bridging loops within our network in this case, because we have routed links between all of these devices. It means that that they act as that boundary, so we don't flood any broadcast traffic across our network. Again, we have traffic load balancing, so we can use all of our links in this topology. Again, same sort of benefit in the last one, and we can still have that sub-second convergence upon an individual link or device failure. Yeah. No, I was just going to say that comparing that to the last topology we looked at, obviously there's no network, there's no virtualized devices, so there's our distribution and core layer devices. They don't share the same fate. We could take out these devices and upgrade them with minimal impact in this environment.
Yeah, so there's a couple of things you said there which are interesting. I think we've shifted down the layer to access layer essentially, haven't we? So we're reducing some of the sort of broadcast domains when we think about, I guess, moving from the kind of physical topology to the logical topology of the network. We've got, you mentioned load balancing there, so I guess the software element of this is looking for the most efficient path or the path that's least congested to send traffic. So you're improving potential performance across the network. Just in terms of SDA or SD access is a product that we're aware of. Is it possible that people, they may have kind of like the previous topology implemented on their network, but they might be using switches that actually are capable of this, and they just haven't implemented it?
Yeah, so I should say, in this slide here, this is the routed access / SD access design. Okay, yeah. And the reason for that is because the network has evolved a little now, and I talked a moment ago about having that constraint of well, the benefit of this is that we don't extend layer 2 throughout our network, which reduces our risk, of any network outages. The downside of that is that there are cases within healthcare that when we need to extend a VLAN right the way across our network. PAX is a very common example of that. So that then becomes a constraint. How do we do that if we've already got layer 2 localized to our access switch? Cisco's SD access architecture enables that kind of stretched pseudo layer 2 domain across a routed access network. So that's why that's in there, because this is kind of an evolution from that design. So yeah, going back to your question, anyway. There will be a lot of customers out there who have compatible hardware for SD access. Block have worked with a number of customers have been provided with DNA center appliances as well, which is the automation platform for this environment, bundled in with some other network switches that they bought. In those cases, it might be that a DNA license subscription is required in order to deploy SD access. We recommend that customer would work with either with a partner or directly with Cisco on coming up with a migration process from their existing traditional network over to an SD access network, or indeed from a routed access network over to their SD access network.
Yeah, so I think the kind of like the hardware that's being sold by the vendors now is really capable of this. And as you said, they're I don't know if they still do. There's definitely been a point in time where Cisco, for example, would be giving out the DNA center appliance with with the product, but you do need that license to be able to take advantage of these features. One of the things we've talked about quite extensively is the sort of like physical topology and the failures that can happen there, and how we can address some of those. What about, you mentioned earlier on, like software faults and broadcast domains? So there's some sort of logical failures that can happen as well. How do we control those?
Yeah, so just going back to, I guess, the pitfalls of that big layer 2 network. There are some issues that we can see, and it's worth just focusing on that a little bit. And there's this. One of the big problems with the layer 2 network is the size of a failure domain. So there's multiple types of failure domain. This what we're seeing at the moment is an example of a layer 2 broadcast domain, which is one type of failure domain. All endpoints are connected here in a single broadcast segment. A broadcast that is sent from a workstation, perhaps connected to one of these access switches down here, is forwarded on every switch in the network, on all ports except the port on which the broadcast was received on. And a network with some redundant links, this kind of topology, bridging loops can occur, and broadcasts can loop endlessly around the network, and that results in high link utilization, high CPUs, and ultimately, network outage. The difference between a big flat layer 2 network, in which case where most of the network shares the same fate, and a routed access network is the size of those failure domains. So in a routed access design, as you can see here, the fault domain or the failure domain is reduced significantly. The broadcasts aren't propagated throughout the network because all the inter-switch connections are layer 3, and they act as a boundary. So devices don't any longer, they don't share that same fate with one another.
Okay.
So we've talked about that sort of routed access design, or perhaps the SD access design, and really that's what we'd be aiming for now for high levels of availability within the healthcare setting. There is a trade-off with this design, however. The layer 2 design that we looked at before is quite simplistic to deploy, reasonably simplistic to operate as well, apart from when we encounter layer 2 type failures that can be quite tricky to troubleshoot. Um, the trade-off with that rooted access or rest access design is an increase in complexity. So we've gone from that reasonably simple network to a network that has a whole host of control plane protocols and data plane protocols. You know, within SD access, we might have an underlay routing protocol. We might have an exterior routing protocol. We could have a control plane like Lisp, or perhaps you know, in other types of architectures we see BGP, EVPN is now quite common, VXLAN. So there's a whole big stack of protocols that you need to understand on how to configure and how to, you know, validate they're operating correctly.
So I think, you know, one of the key things here is, you know, there's complexity introduced in really the configuration of each device. But I'm guessing you're going to say that DNA Center kind of like controls that complexity by applying consistent configurations to devices and checking that they're compliant. Is that how it works?
Yeah, again, focusing on Cisco solutions. So with an SD access, as you can see here, the way to kind of tackle that complexity is being able to use the automation platform, which is a part of the solution. So here we've got DNA Center. The DNA Center is pushing out best practice configuration. You know, all of those hundreds of lines worth of config that we need in order to put together our SD access network. DNA Center can push that out to multiple devices. So we know we've got the right configuration on there. The configuration is consistent across our network. And then there's something of feedback from the network as well. We receive telemetry in from those devices into DNA Center to ensure that our network is functional as well. So although we need to build the network using all those protocols, you know, we've got a tool in order to apply those configurations consistently and understand that they're working correctly.
So that's really helping overcome the complexity by giving you that tool to really manage it across the estate where that's installed. Okay, thanks, Joe. So I mean, we've talked a lot about physical connectivity and about the logical stuff. In my experience, you know, all of this is really underpinned by redundant power to your cabs and your switches. Just what options have we got there in terms of providing, you know, resilient power to our network stacks?
Yeah, I'll skip through this rather quickly, but we've got, it's common to use to use stacks for access layer connectivity nowadays. Just quickly to mention that the Cisco stack power solution. This is for anybody with compatible Cisco Catalyst switches. It's a great way to increase availability at the access layer. You know, power outages are relatively common, and you know, this solution might be able to keep the the access layer switch running, keep the lights on, so to speak. So we can have up to 4 switches that are connected in a stack power ring. And what does that mean? That means that all of the power from all of the stack power members are pulled together. The failure of a single PSU just reduces the overall power budget, but the stack power members and connected PoE devices could remain online, provided there's enough power, available to within the pooled power budget to keep them running. So yeah, you can, as you can see here, you can stack up to 4 members using stack power. This is separate from a data stack, by the way. So you might have 8 switches in a data stack, but you could have 2 4-member stack power rings within that data stack.
Okay, so as long as our cab's got resilient power coming in separate feeds from different directions, we can power each side of the the sort of stack power ring, if you will, and then you'll get a resilient stack out of that. Brilliant. Okay.
Yeah. And just briefly there's a few just recommendations on here for data stacking as well. So some of them are well commonly known. I just want to highlight one really, and just it's important just to have multiple logical switches in a given area for resilience. We'll see that in a moment. We're going to touch on some wireless high availability aspects, and if possible, if we have an area where we require, significant port density, then if possible, if we have enough fiber uplinks available, create, several logical switch stacks in that area so we can spread devices, and we'll see in a moment, access points across these switches to increase availability.
Okay, great. So, I mean, we've talked a lot about physical connectivity and some of the logical approaches to network design. Redundant power is obviously really, really important too. But I just want to come back to that point we mentioned earlier on when we think about the access layer. If we've got somebody who's physically connected to an access layer switch that fails, they still lose connectivity. So I can remember we would do sort of salt and pepper designs where, that computer might go off if you had an outage or you had to do some planned maintenance. The next one would be okay because that was basically cabled to a different computer. Is there a way to overcome that?
Yeah, and that is the problem with wide connectivity. Typically, the endpoints they're connecting in here have just got a single uplink, a single network interface that connects into the access layer. But I have worked with some customers, and they've been able to, identify certain wired endpoints of a particular type and spread them across multiple different access layer switches, and that's helped them, to be able to secure downtime when they want to, do like a software upgrade and access switch. But still less keen, because it does mean 50% of our particular wired endpoint type is going to be offline, perhaps where we have two logical switches that are serving that area. So yeah, the recommendation here, and obviously it's more of a strategy than anything else, is to leverage wireless as much as possible for our endpoints in order to take advantage of some of the high availability features that are sort of baked into to wireless.
Do you mean that as a fallback position, or do you mean that as just do wireless?
Yeah, I mean, more of a default, really. So if we have the option to leverage wireless for endpoint connectivity, recommend that we do that. And so moving on to the reasons why that is, wireless obviously provides us with some mobility for endpoints, and that's traditionally what it's used for. However, it can be a really good tool for high availability as well. With a good wireless AP design and some of the sort of RF type high availability features, you can keep endpoints online even where we have wireless access point failures, or even failures within the wired access layer as well. If we just focus again on Cisco's wireless offering, there's a feature in there which is very commonly used, called Radio Resource Manager, or RRM, and that's going to provide our RF high availability. First off, it should just say that it does also rely upon us having a good wireless AP design. So it's really crucial that first off, before anything else, conduct a wireless site survey. That's absolutely critical for a good wireless design. Following on for that, ensure that, particularly with the Cisco product, that we've got RRM enabled. And what's that going to give us? So in this kind of environment, you can see we've got a floor here. We've got several access points and each of those access points have got their own coverage cell covering a particular area. If we have a failure and we've got these features turned on, we've got a good wireless design, then we can the RRM feature can increase the power of any of our neighboring access points within 90 seconds, and clients can roam from the failed access point over to a surviving one. So that's obviously going back to that discussion on the wide access layer. If we have a switch failure and you're connected into that switch, and you're offline until we can restore that switch. In contrast to the wireless, we can lose some of our network components like perhaps this wireless access point or an access switch, and clients can remain connected throughout.
Great. Yeah, I think, for me, it's a bit of a change in thinking. It says for wired devices, we just wired them. Which probably
Yeah.
seems quite strange nowadays, but and yeah, I know obviously we've been through this already, Joe, but I was sort of quite surprised. I thought, why didn't I think of that? My house has got like a mesh Wi-Fi system. It's nowhere near as complicated or as advanced as what we've got in healthcare, but you can just roam around the house, and if you just turn one off, it just carries on working. I don't know why it never dawned on me to think about that in the healthcare setting, and to kind of make wireless the sort of default for the desktop, if you will, because a lot of stuff's going on the wired, the wireless network now anyway. Yeah, really interesting, different thinking for me, that one.
So yeah, just a couple of points on that. Of course, that there are some some other requirements here to ensure that we get that high availability. Where we've got, I think I said earlier as well. So if we've got an area that's served by a single access switch, and we've got all of our APs connected, as you can see here. If all these APs were connected into the same access switch, and that access layer switch went offline, then of course we'd lose all of our APs in that area, which would not be good, and we would not have any high availability at all. So yeah, absolutely important that when we're designing our wireless network, that we ensure that our APs are physically connected into separate access layer switches, so that we can take them out of service, or perhaps there's an unplanned failure, and they can continue to operate.
So back to salt and pepper, but for your APs rather than your access layer devices, I suppose, really.
Yeah, exactly that. I won't labour on any of this other wireless availability stuff. Just to say, that still the recommendation for particularly in a Cisco wireless deployment is to deploy wireless LAN controllers in a HA pair. So we're looking at physical connectivity of APs a moment ago, physical connectivity of wireless controllers. If we deploy these in a high availability pair using stateful switchover, we can ensure that we can lose a particular wireless LAN controller, one out of that pair, and clients will seamlessly fail over from one to the other. So that, that's still the recommended design in terms of high availability for our wireless LAN controllers. And of course, it's important that we again connect them into separate logical layers of our wired network as well. As you can see here, we've got our wireless LAN controllers connected into a services block. So that that could be that could be something that's connected to our core layer. Perhaps we've got our core a layer acting as a services block as well. We might have other things connected in there, such as identity services, or a DNA center appliance for running access. But yeah, the key thing is obviously we've got them connected into separate physical switches.
Right.
And just one final thing on that, we kind of said earlier that we do see some issues sometimes where we use this chassis virtualization, within the core layer of our network, within the wired network. We talked about those virtualized chassis. We can still run into the same sort of issue here, within the wireless network. Perhaps this pair of wireless LAN controllers fails at the same time. It's a rare occurrence, but it does happen. So just to say, there is a possibility, within the wireless Cisco wireless architecture, that we can have a SSO with N+1 design. So we can have our access points that are primarily registering with our wireless LAN controllers, our HA pair, but they could fall over to a secondary wireless LAN controller if needs be.
Okay, so belt and braces on that one then, really.
Yeah, absolutely. And just final thing on wireless, particularly on the Catalyst 9800 platform, there's a great feature in there for in-service software upgrades. So this is a relatively new thing to wireless. In the past, we've had to, if we want to do a software upgrade, we have to upgrade all of our access points in one go, essentially take down the wireless network. With the ISSU feature, we can upgrade the code on our standby wireless LAN controller. We can bring that back up again on the new code, establish our HA relationship with the other peer wireless LAN controller. That can upgrade as well without any impact to the to wireless network. And then there's the AP upgrades, which is kind of like part two. So APs are upgraded. Not as a whole, but a percentage of the AP estate. We use it uses the RRM functionality there to identify candidate APs that can be upgraded with minimal impact to
It's looking for that sort of peer Wi-Fi relationship almost to not take down the network and upgrade APs.
Yeah, exactly. So clients can still move over to an AP that isn't being upgraded at that time.
Okay, great. Thanks, Joe. It's really, really interesting. So, probably got about 5 minutes, maybe a little bit more, just to go through the thousand eyes thing. So, we've talked about some of the physical and logical approaches to designing high availability and how we can leverage Wi-Fi. As you said at the start of the presentation, really, 99.99 is still 56 minutes or whatever it was. 99.999 is going to be about 5 minutes downtime per year. So there is still the risk of downtime. How do we pinpoint that and get to the sort of resolution as quickly as possible?
Yeah, so a slight deviation, I guess, from the topic of high availability, but it kind of fits in here anyway because obviously we can carefully put together our fully resilient network, and obviously we hope this can respond to all types of individual device or link failures. But our network can extend now, over the WAN or more commonly now, into public cloud. So the path between an endpoint on the network and the application that they're trying to consume, that can have hops that within our own network, and also network that's outside of our control. So that's where Thousand Eyes comes in. It's a great tool for monitoring end user experience. We can set up application type probes that can really help us out where we need to identify if there's an issue within our own network or if there's an issue outside of our network in a different hop. It gives us that visibility to be able to troubleshoot that. I won't go in detail around the product, but I will say that it's a SaaS-based platform. So you manage the platform and configure our tests within the cloud portal. It requires agents to be installed, and these are our vantage point in the network. So all our tests are sourced from here. There's a few different agent types. There's an endpoint agent that we can put directly onto an endpoint, Windows or Mac. There's an enterprise agent that can be deployed within our data center as a virtual machine, as an option even for a Docker container that goes directly onto a compatible Catalyst 9000 series switch using their application hosting. And there's also an option for a cloud agent directly as well that goes directly into public cloud. So yeah, I just really wanted to talk about a particular use case or a real world example where we've seen this useful within a customer's network. So Block were working with a customer. They had an application that was hosted on premise, a clinical application, and the provider offered a cloud alternative. In this case, the app was to be migrated over to Microsoft Azure, and it's going to be hosted by a third-party company. The trust that were going to consume the app that already had their own express route. They're already making use of Azure for their own workloads. In the proposed design, the express route was going to be used to connect to the third-party app hosted in Azure, and secured with an IPsec tunnel. So yeah, that was the that's kind of the network design for the migrated or public cloud hosted version of the app. So that was all fine. So when the customer went live with this application, it followed a few months of worth of testing phases, which had all gone well. There was a successful go live of the cloud hosted app. And all was well until a few months later, when there was some reports of some application outages that had come in. And users were complaining that there was connectivity issues. So what happened after that? Straight away, there was an end-to-end investigation. Now, obviously, as you can see, there's a few components in there. Obviously, there's a third party that hosting the app. There's Microsoft, who provide the public cloud Azure. There's an express route connectivity from the which is a direct connectivity into Microsoft Azure from the customer, and that was provided by a service provider. So there's a whole load of people that are involved. So the end-to-end investigation involved the network trust, the third party service providers, Microsoft, and ultimately a few weeks later, the application was restored maybe with a couple of hours, I think, in this instance. However, the root cause was never identified. There was a whole load of people investigating the issue, but they couldn't.
And it was nobody's fault. I've been there so many times, you've got 4 or 5 vendors in a kind of root cause analysis, and nobody's owning up to whose problem it is. So go on. How do we help?
So yeah, we started working with the customer. We leveraged Thousand Eyes. We deployed Thousand Eyes, and what happened next time is that there was another outage a few weeks later after we'd put Thousand Eyes in. This time Thousand Eyes sent out an alert email so that the Trust Zone network team and blocks operation team were notified. Immediately there was some kind of issue that had been identified with application connectivity. So straight away support teams can get into troubleshooting the issue. They went direct from the email following a link that shows a path visualization, which I'll show you in a moment. Straight away, the network engineer that was investigating was able to locate the time period of interest and really drill down onto what happened during that time period. At the same time, of course, the application is down. Users start to report the issues, but now we've had a head start. We're not waiting for those tickets to come in. We've been alerted in advance. And what happened this time? The root cause was identified. The path visualization tool, which I took look at in a moment, that revealed 100% packet loss within the service provider's network. So this was over the customer's express route, and that provided a load of quite detailed information about on which device failed, IP address of that device, the service provider's ASN. So the information was then passed on to the service provider. They investigated what happened within that network. Was there a lack of resilience within the network, or was it just like a failure that restored pretty quickly afterwards? But it was quicker resolution, fewer teams were involved. And just to show you that path visualization, this is what it looks like. As you can see here, we had a test that was running. It showed that we had 100% packet loss within the time that the issues were reported. Down at the bottom here, we've got our test source on the left, which is our agent, and our destination application on the right, which is this green one here. And each of these dots in the middle is hops. So that they may be hops within our own network or hops within the service provider network. And we can see in this case, this red ring was around a Virgin Media router. In this case, it was 100% packet loss whenever traffic was traversing this particular path, and it gives us all information that we need to pass on to the service provider to investigate the issue in greater detail. So
And
that's
so,
it. Obviously, really quick, but I just wanted to show that that it is a really useful tool for
yeah,
diagnosing
and
those
I
issues.
think that's really useful and really relevant. When we come back to that point about there is always a very small fraction of time where you could have an outage, and being able to pinpoint that as quickly as possible. Clearly, what we've been able to do here with Thousand Eyes is really, really important. And again, Thousand Eyes, is that a product people will have, or do they need to buy that? How is that going to
Um,
work?
so yeah, it's a SaaS-based product. There's no licensing for the platform itself. It's usage-based licensing. So and that's based on the number of agents deployed and the number of tests that are being run and the frequency that they're running on. So yeah, it's a usage-based licensing. So some customers may have it bundled in with if
Yeah.
they have DNA subscriptions as well for Cisco.
Yeah,
Wide
I've talked
network.
to a couple of colleagues who've, got Cisco DNA Center and then didn't realize they had this. So I don't think it's necessarily shouted about, but if you've got that product, you may well have Thousand Eyes already, and yeah, just need a bit of help getting it configured, I guess, really. So yeah, I think we're on to the questions, aren't we? So
Q&A.
we've got a couple of minutes. We haven't had any questions come through yet. Okay, so there's a question just come through on the chat now. Sorry, looking over that way to see see the questions come through. So somebody's asked, do we need this level of availability across all locations? I think the answer to that is that's probably one for me actually to answer, isn't it, Joe? So I think it depends on what your care setting is really. What I would imagine is you need to probably provide this level of resilience and availability in a very clinical critical environment, so in an acute setting or even in a large hospital. What you might find is that you don't need this kind of level of resilience at a local clinical resource centre. Whilst it might be lovely to have that, I think if you work in healthcare or any organisation, you realise you have to make prioritisation decisions and sacrifices in some respects, and you need to work out what's going to work well for your organisation. I would suggest that starts with a kind of review of what the services are at the location and what the impact of failure of those services is, and those things need to be considered with I suppose the customer really, and just understand the impact to them if those things fail.
Yeah, yeah, absolutely. It's that balance, isn't it? I think we looked at probably large scale topologies today, but there are ways of introducing resilience on a smaller scale
Mm.
for some remote sites. But yeah, like you say, it's that balance, isn't it?
Okay, no more questions. All right. Well,
Okay.
thanks very much, Joe. It's been great working with you on this webinar. So
Thank you.
appreciate all the effort you've put into it, and thanks to everyone who's joined us today. I hope you enjoyed it. And yeah, if anyone's got any questions, please reach out to your account manager, or you can contact me via LinkedIn. I'm sure you can hunt me down if you found the webinar. So it'd be good to hear from you if you've got any questions or you'd like to talk about this further. So thanks very much, everyone, and hope you can join us for future webinars.
Thanks all.
Cheers.